This is a very brief tutorial on balancing chemical equations. This is a very brief review of key points in balancing chemical equations. Before I get going, I'll just remind you that the law of conservation of mass says that the mass of all of the reactants summed together equals the mass of all of the products summed together. So because of the law of conservation of mass, all of the atoms that appear on the reactant side of an equation must also appear on the product side. Now, of course, they're going to be joined together in different ways, but if you count individual atoms, they should be the same on both sides. All right, so chemical equations, just so that you know the shorthand methods that chemists use. The reactants are on the left-hand side of the arrow. The products are on the right-hand side of the arrow. Some of the shorthand symbols that are used, an arrow is used. Arrow means yields or makes or produces. The state of matter sometimes is included with the reactants and products. So S is solid, L is liquid, G is gas. AQ is aqueous, which means that something is dissolved in water. All right, the biggest rule to remember when you're balancing a chemical equation. So let's say that we were given this, they call it a skeleton equation when it is not balanced. It's clearly not balanced because you have 2 hydrogens on the reactant side and 2 oxygens on the reactant side. On the product side, you also have 2 hydrogens, so the hydrogens are balanced, but you only have 1 oxygen on the product side. So it is not balanced. The main rule that you need to remember when you're balancing equations is never, ever, ever, under any circumstances, change a subscript. So, for example, you're given the skeleton equation here. You're told the product is water. You cannot change that formula of H2O to something, I just made this up, like H2H2 in an effort to balance the atoms on both sides of the arrow. Okay? You cannot change what the substances are. The only thing you can do while you're balancing an equation is to change the coefficients. Those are the big numbers in front of the formulas, of the compounds. All right, these rules, some students ignore them and just kind of dive in and try to randomly balance an equation. That'll work for easy equations. You get to a hard one and you can chase your tail for half an hour. So if you follow this order of balancing atoms, I can guarantee you I've never seen it not work. So you want to balance metals first. Where are the metals? Those are all elements to the left of the stair step. Balance those before anything else. Balance polyatomic ions second. So polyatomic ions, for example, sulfate. Okay. Balance them as a group. If you have a polyatomic atom on the reactant side and on the product side, instead of balancing individual elements like sulfur and oxygen, balance the whole group. How many SO4 groups are on the reactant side? Make sure they're the same number of SO4 groups on the product side. Really makes things easier. And finally, save oxygen to balance until very last. It's a bear. And save hydrogen to balance until next to last. So the bottom line is you're going to do metals, then polyatomics, then all elements other than oxygen and hydrogen. All right, so let's do some examples. This is how I would do. Now, I know that some teachers, when they first teach it, have you make this really complex table where you keep track of atoms on both sides of the equation. If you want to do that, go ahead. I find that more confusing than helpful. What I would do is I would look at this equation and I would say, are there any metals? I'd have the periodic table in front of me. Yes, there is aluminum. Therefore, I have to balance the metals first. I have 2 aluminum atoms on the product side. I can't change subscripts over here. I cannot add a subscript. Now let's see if I can figure out how to erase. There we go. I can't change a subscript. All I can do is add numbers in these coefficient areas. So I'm going to add a 2 here. That balances my aluminum atoms on both sides of the arrow. All I have left is bromine. I have 6 on the product side and 2 on the reactant side. I'm going to put a 3 here, multiply coefficients by subscripts to see how many total atoms. So now I have 6 bromine atoms on both sides, and guess what? The reaction's balanced. If there's a coefficient of 1, it's understood that it's a 1. You don't have to show it. All right, here are some other examples. If you know how to balance basically and it's just been a while, I would suggest pausing the video and seeing if you can balance these. If you haven't really done this before, then you can watch me do a couple more samples. This first reaction is a combustion reaction. I know that because it has a reactant of oxygen. The products of combustion are always the same. They're carbon dioxide and water. Combustion is one of the hardest types of reactions to balance, not necessarily this specific one, but in general. There's a special little rule I use for balancing combustion. I balance the elements in alphabetical order. Carbon first, then hydrogen, then oxygen. CHO. So there are 3 carbons on the reactant side, so I'm going to put a 3 coefficient in front of carbon dioxide. Balance hydrogen second. There are 8 hydrogens on the reactant side, so I'm going to add a 4. 4 times 2 is 8, so the hydrogens are now balanced. What I'm getting ready to do is why combustion reactions are tricky to balance. You now have to balance oxygen. Be very careful because on the product side there are 2 sources of oxygen. There's oxygen present in both products, so make sure you add them both. From carbon dioxide, I have 3 times 2 or 6 oxygen atoms. From water, I have 4 times 2 or 8 oxygen. So I have a total of 6 plus 8 or 14 oxygen on the product side. How do I get 14 oxygen on the reactant side? Well, 7 times 2 is 14. So my final balanced coefficients, there's a 1 here, a 7 in front of the oxygen, 3 in front of carbon dioxide, and 4 in front of water. Onward to the next one. I'm going to go a little faster. The metal is silver. I'm going to balance that first. Balance polyatomic second. There's 1 SO4 group on the reactant side, and there's 1 SO4 group on the product side. Chlorine, I'm going to save hydrogen and oxygen till last. Obviously, the oxygen and sulfate doesn't play into that role because it's part of a polyatomic. There's 1 chlorine on the reactant side, but there are 2 chlorines on the product side. So I need to put a coefficient of 2 here to make 2 chlorine. The only thing that's left to balance now are the hydrogen atoms. I have 2 hydrogen atoms in the reactant side and 2 hydrogen atoms in the product side. This is now balanced. That was a bad star. All right. So here are a couple of other reactions. Again, what I would recommend doing now is that you put the video on pause, give it a shot yourself. It's really important. As easy as it may look to you, you need to do some yourself. So I'm going to go through and work them now. It's the combustion, so CHO, carbon first, so I'm going to put a 4 here. There are 10 hydrogen on the reactant side, so I will put a 5 here. That leaves me with oxygen to balance. Remember to total all of the oxygen from both carbon dioxide and water. So I have 4 times 2 or 8 oxygen from carbon dioxide and 5 times 2 or 10 oxygen from water. So I have a total of 18 oxygen on the product side. So in order to get 18 oxygen on the reactant side, I have to put a 9 there. That reaction's balanced. All right, the next one. We don't have any metals. Well, yeah, we No, boron is a metalloid. We don't have any metals. We don't have any polyatomics, so I guess I'll do boron first. If I put a 2, on the product side now, I have 2 times 2 or 4 boron, just like I do on the reactant side. Save oxygen till very last. So I'm going to do hydrogen next. 10 hydrogen on the reactant side. So I'm going to put a 5 in front of water. 5 times 2 is 10. I need to count oxygen now, and it looks like it's going to be a little tricky. Let's see. On the product side, I have 2 times 3 or 6 oxygen plus 5 times 1 or 5 more oxygen. So I have 11 oxygen. Ooh, doesn't really look like 11 on the product side. This is actually really tricky and really important. It's a higher level balancing problem. I want to get 11 oxygen on the reactant side. And how do I do that if I have O2? If you need an odd number of oxygen, what you do is put how many oxygen you need, that's 11, divided by 2, so your coefficient is now a fraction, 11 divided by 2. You can't leave it like that. That is a balanced reaction. You can't leave it in fractional form. So what you need to do whenever you have to play this trick is multiply all of the coefficients in the entire reaction by 2. That will get rid of the fraction. And so what will I have? Well, it's assumed to be a 1 originally in front of the boron. So when I multiply that by 2, I've got 2B4H10, tetraboron decahydride. All right, and when I multiply 11 halves by 2, I get 11. So I have 11 oxygen. When I multiply the product side, 2 times 2, so now I have 4 of the diboron trioxide. 5 times 2, and I have 10 water. And your final challenge, here's the last slide. This would be a good free response to have on your test. Can you take a word equation and convert it to a chemical equation with formulas and then balance it? So that checks your mastery of nomenclature, checks your mastery of writing formulas and balancing. So I recommend turning the video off, giving that a shot, and seeing how you do. And I'll create another page now and work it out for you. Alright, so the first reactant was sodium phosphate. And sodium phosphate reacts with iron 3 oxide. So let's see if we can get those. Sodium, right? Phosphate. It ends in 8, which means it's a polyatomic. Anything that ends in 8 or ite is a polyatomic, so you need to look that up. Phosphate is PO4 with a charge of 3-. Sodium is in group 1 of the periodic table. When they become ions, they have a charge of +1. Just put that there. All right, you need to balance these 2 ions so that the overall charge of the compound they make is 0. In other words, there need to be as much positive charge as there is negative charge. So I need a total positive charge of +3. I do that by adding 2 more sodium ions. You can have as many ions as you want to balance. So the formula that gives me is Na3PO4. You can also arrive at that by doing the crisscross rule. So if you had this written, crisscross rule is you take the charge and move it catty corner, diagonal down as a subscript. So this 1 from the charge on sodium would come down here, and the 3 from the charge on phosphate would come down as a subscript for sodium. So you'd still get the same thing, Na3, PO4, 1. You don't have to put the 1 there, it's understood. All right, iron 3 oxide. Remember what the Roman numeral means? That means that's the charge on the iron. Iron is a transition metal and it needs the Roman numeral. But to write the formula, you always start by writing the ions with their charges. Oxide is from oxygen. It ends in IDE, which means it's just an element from the periodic table. Oxygen is in a group that when the elements become ions, they have a charge of -2. So you can either do the crisscross rule, which is probably easier in this case. So the 2 comes down as a subscript in iron, the 3 comes down as a subscript in oxygen. There's the formula for iron 3 oxide. Alrighty, so once you have all the formula written correctly, you need to balance the overall chemical equation. If for some reason you get a chemical equation that will not balance, no matter what you did, 99% of the time that's because you have one of the formulas balanced incorrectly. So go back and check your formula. Alright, so I'm going to follow the same rules. I'm going to balance the metals first. You have 2 metals, sodium and iron. Doesn't matter which one you do first. When you have a situation like sodium, where you have an odd number of atoms on one side and even on the other side, get a common factor, multiply them together. Your common 3 times 2 is 6, so put whatever coefficient you need to have 6 sodium on both sides. That would be a 2 here and a 3 here. Now I have 6 sodiums on both sides. Alright, let's see. Iron I'm going to do next. I have 2 iron on the reactant side, so I'm going to put a 2 in front of this iron. I think I'm all set. I'm going to check the rest of the atoms. I have polyatomic. Phosphate is a polyatomic. I have 2 PO4 groups on the reactant side and 2 PO4 groups on the product side. Oh, I still have oxygen to check, don't I? Free oxygen. I have 3 oxygen on the reactant side and 3 oxygen on the product side. I am balanced. Very good. End of video.